Hello friends, continuing with the unit magnetic effect of electric current, here is part 3 of the unit. In the earlier two parts, you have seen that a current carrying conductor exerts a force on magnet, and conversely the magnet exerts a force on the current carrying conductor. In the present part 3, we will study the application of the force of magnetic field on the current carrying conductor. So the force is utilized in design of an electric motor and a galvanometer. So these are two devices which make use of force of the magnetic field on a current carrying conductor. Let's discuss the electric motor first. The electric motor is a device which transforms electrical energy to mechanical energy. That is, the input energy is the electrical energy and the output energy is mechanical energy, because the motor is supposed to rotate with the help of electric current. Electric motor is an important and integral part of electric fans, air conditioners, refrigerators, mixers, washing machines, electric trains, other electric vehicles and computers, etc. Wherever you see the motion due to electric current, an electric motor is at work. How does the motor work? Let us probe. The essential parts of an electric motor are shown in the figure. The diagram is an oversimplified version of electric motor and explains only the principle of electric motor. The parts are coil ABCD, rectangular in shape in this diagram. A magnet NS, the coil is in the field of the magnet. Split rings P and Q which rotate with the coil. Brushes X and Y, these are fixed. Axle on which the system works. The motor consists of rectangular coil ABCD of an insulated copper wire. Here only one turn, a single turn has been shown. In fact, in actual motor, the coil ABCD consists of a large number of turns. The coil is placed between two poles of a magnet with its arms AB and CD perpendicular to direction of the magnetic field. Magnetic field, as you can see in the diagram, from north to south is from left to right, and AB and CD arms, they are perpendicular to the direction of the magnetic field. The ends of the coil, that is end A and end D, they are connected to a split ring. You can see here in the diagram we have a ring which is cut into two parts. These parts are insulated from each other and also from the axle. You can see there is a gray layer in the lowermost parts of the split ring. The upper reddish part is conducting. The halves P and Q of the split ring are insulated and they are attached to an axle. The external conducting edges of the split rings, they are in constant contact with two conducting but stationary brushes X and Y. So the split ring will rotate with the coil, but the brushes will remain fixed. Let's see brief working. The current in the coil ABCD enters from the source battery through conducting brush X and flows back to the battery through brush Y. Here X is connected to the positive terminal and Y is connected to the negative terminal of the battery. So when you insert the key, you will have current flowing along ABCD through the coil. In AB it flows from A to B, and in CD it flows from C to D. Here AB and CD are the two arms which are placed in the field of the magnet. When they carry current, the magnetic field exerts a force on AB and CD. We have to see the direction of the forces on AB and CD. For the purpose, we have to use Fleming's left hand rule. The diagram regarding the use of Fleming's left hand rule, that is how you have to use the three fingers, the forefinger, the central finger and thumb of the left hand, is given for your reference. The forefinger, as studied earlier, points in the direction of field, the central finger in the direction of current, then the thumb gives the direction of the force. If you apply the force to part AB of the coil, the force on AB acts downward. The arrow shows the direction of the force. Similarly, if you apply the rule to part CD of the coil ABCD, the force on CD acts in the upward direction. So, the coil and the axle mounted free to turn about the axis rotate anti-clockwise. See the forces acting on the coil, they make it turn in the anti-clock direction as seen from the side of the axle. After half rotation, the diagram is on the screen. So CD now is on the left hand side and AB is on the right hand side. The current reverses direction. Now through the coil it is flowing from D to C and coming out from part AB. The direction of current we can say is DCBA. A device here, the split ring, reverses the direction of flow of current through the circuit. This device is called a commutator. So the split ring is termed as split ring commutator. Purpose, function, as said earlier, it is used to reverse the direction of current through the coil ABCD. You can see how the reversal takes place. Earlier P was in contact with X, Q was in contact with Y. After half rotation, Q comes in contact with X and P comes in contact with Y, resulting in reversal of direction of current from ABCD to DCBA as shown. The reversal of current also reverses the direction of forces acting on AB and CD. So arm AB is now pushed up and CD is pushed downward. The direction of forces is shown in the diagram. The coil and the axle therefore continue to rotate in the same direction, that is anti-clockwise direction. The reversal of current is repeated after every half rotation, resulting in continuous reversal of direction of current, but the coil continues to rotate in the same direction along with the axle. In commercial motors, we make use of an electromagnet in place of permanent magnet that helps in increasing the strength of the magnet, and we can also control the strength of the magnet if desired by changing the magnitude of current. There is a large number of turns of conducting wire in the current carrying coil. We have a soft iron core on which we mount the coil. The soft iron core along with the coil, they are called armature. So armature consists of a soft iron core on which we wound the coil. We have the soft iron core used enhances the power of the motor because the magnetic field gets multiplied, increased, strengthened with the use of the soft iron core. So this is how an electric motor works and helps to convert electric energy to mechanical energy. A galvanometer is another instrument which works on the basis of force of magnetic field on current carrying conductor. Galvanometer basically is used to detect and measure current flowing in an electric circuit. We place the galvanometer in the circuit. When there's a coil in the galvanometer, it's an essential part and it is placed in magnetic field. When current is passed through the coil, the forces act on the coil placed in the magnetic field, which turns, which gets deflected, and that deflection is recorded and measured from the position of the pointer on the scale. So this gives us the magnitude of the electric current. Here are a few problems for practice to reinforce and test check what you have learned in this particular unit. Remember to subscribe to our YouTube channel so that you continuously get the notifications of the lessons covered in subsequent videos. For feedback, you can write to the mail ID on your screen. Thanks for watching and being with us. Happy learning.